us take an example by which I will be able to explain you the concept of toppling. Toppling. For the sake of simplicity, you take a cubical box of height h and breadth b. More generally, the box may be a rectangular solid. It's placed on a rough horizontal surface. You apply force at a distance y from the ground. So that the box remains stationary. When it remains stationary, velocity of the center of mass is 0. When center of mass velocity is 0, acceleration of the center of mass also will be equal to 0. No sliding. For the stationary box, velocity is 0 of the center of mass and angular velocity of the box also will be equal to 0. Then only you can say the box is stationary, motionless. No linear motion, no angular motion. We say 0, omega 0. Therefore, it is a clear-cut case of translational equilibrium and rotational equilibrium. It is translational equilibrium because center of mass velocity is 0, no linear motion. It is rotational equilibrium because there is no angular motion, omega 0, because the box is stationary. It is given. From this you have to start. Since the box is stationary, this is 0, omega 0, therefore it can, or it possesses both types of equilibrium, rotational and translational. Let us draw the FBD. At the center of mass, gravity acts. Normal reaction acts. Let us assume that normal reaction acts at a distance x from the point, let it be P. From this edge, let it be x. You may be thinking normal reaction will pass through the center of mass, but it is not. I will show you why. Now we have two equations, force equation and torque equation. Since acceleration of the center of mass is equal to derivative of the velocity of the center of mass, and velocity of the center of mass is 0, therefore the center of mass acceleration will be equal to 0. Since omega is 0, alpha as a derivative of omega will be 0. From the given condition, we have found the accelerations, both linear and angular acceleration. Fourth equation can be written by using the acceleration of the center of mass. F is equal to ma. It has two components. Fx is equal to mx, Fy is equal to may. A is the acceleration of the center of mass. Since it is stationary, AC is 0, therefore both ACX and ACY will be equal to 0. The components of acceleration of the center of mass in both directions. X direction it is 0, Y direction it is 0. Therefore, net force acting on the body along X direction will be 0, along Y direction also it will be 0. What is the net force acting on the body? Along X direction, one force is pushing in this direction, and since the surface is rough and the body is not sliding, the static force of friction which prevents the relative sliding must act in backward direction or leftward direction. So net force will be F minus Fs. In horizontal direction can be equated to 0. So we will get the frictional force is equal to the applied force. Equation number 1. Along y direction, we have two forces. Normal reaction up and mg down minus j cap. So n is equal to mg. That is equation number 2. Two force equations we are getting. Next, you have to write the torque equation. About z axis passing through the center of mass. You can choose. You can choose this point, you can choose this point, you can choose any other point outside, as I talked about this matter in the last example. Let us choose center of mass point. If you choose center of mass point, the gravity cannot produce a torque about the center of mass. The torque is produced by this force, and this force. Applied force, normal reaction, and static force of friction. Force of static friction. Well, this will be equal to torque due to the applied force, torque due to gravity, torque due to normal reaction, torque due to tangential reaction force, that is none other than the force of static friction, will be equal to 0. Because alpha is 0, is equal to I into IC into alpha. Since alpha is 0, so we can equate the torque to 0. Since gravity passes through the center of mass, we can set tau g is 0. Now the three torques will be added to get 0. Let us assume that from the ground the force is acting at a distance y. In this way also you can write, or from the center of mass also you can take y. If you take this as y, this is h, this will be h by 2. This is the line of action, this is the perpendicular distance, that is equal to y minus h by 2. The perpendicular distance from the reference point onto the line of action of this force is P is equal to y minus h by 2. So, this applied force produces clockwise torque. This torque is clockwise, F into y minus h by 2 minus kf plus normal reaction produces a torque which is equal to normal reaction into this distance. This is the line of action of the normal reaction and this is the perpendicular distance. This perpendicular distance will be equal to, this distance is b by 2, this distance we have assumed x. This perpendicular distance is different, this perpendicular distance is different. Therefore, normal reaction tries to rotate it in anticlockwise manner with a torque and into this perpendicular distance, that is equal to b by 2 minus x is equal to a plus this is over, this is over. Now consider the force, frictional force, static friction. This will produce a torque about the center of mass. This is the line of action of the force of friction, this is the reference point and this perpendicular distance will be equal to h by 2. Static friction about this point will be inward or clockwise because this force tends to rotate the box about the center of mass in clockwise manner with a torque of magnitude Fs into this distance is h by 2 in minus k cap direction. When these three torques are added, we are getting 0. So, this gives us the equation f y minus h by 2 plus Fs h by 2 will be equal to n b by 2 minus x, equation number 3, where the frictional force we can find from equation 1 and normal reaction we can find from equation 2. If you substitute the values of the frictional force and normal reaction force from equation 1 and 2 in equation 3, from force equations to torque equation, we are getting, substitute by substituting Fs is equal to F from equation 1, N is equal to mg from equation 2, N equation 3. These are the force equations, they are the torque equations, 3 equations we are getting. We have F the y minus h by 2 plus what is Fs? That is equal to the applied force magnitude wise into h by 2 is equal to the normal reaction will be equal to mg magnitude wise into b by 2 minus x, and you can get the value of x. So b by 2 minus x will be equal to f, take common, y minus h by 2 plus h by 2 will be y by mg. Therefore, x is not equal to b by 2. So, x will be equal to b by 2 minus fy by mg. That's interesting. So, obviously, this is less than b by 2. I posed a question. The student may think that the normal reaction will pass through the center of mass, but it is not. Because x is less than b by 2. The normal reaction is shifted towards this edge. And when that normal reaction will coincide or will pass through this point P, that is the condition when x will be equal to 0, the normal reaction will pass through the point P. Putting x is 0, putting x is equal to 0, we are getting b by 2 minus fy by mg. So, f is equal to mgb by 2y. When the force will be equal to this much, the normal reaction will be shifted gradually towards the edge, and exactly when the force, applied force will be exactly equal to this, the normal reaction will pass through this point. Needless to mention, it is always normal. In that case, what will happen? Let me discuss. When the normal reaction will pass through the edge P, gravity is always acting at the center of mass. You are pushing here. So, physically we can say that the body will lose contact. The body will lose contact. All the points will lose contact except this point. All points except the edge points will lose contact with the ground. And then we can say that the body is under toppling. Then we can say that the body is about to topple. Because the example name is given as example of toppling. This is coming under the equilibrium of rigid body. So, the body is beginning to topple. I can demonstrate by taking this cubical object a rectangular object. Apply force, it slide, but we are preventing the sliding. Therefore, the applied force and the frictional force must be equal and opposite. Sufficient friction will be there so that it won't slide. If it's not sliding, for a particular force, all points will lose contact with the surface. All points will lose contact with the surface except the points of this edge. This is the edge point, or you can say like that, or you can put it like this. You are applying a force here. When you go on increasing the force from 0, provided there is sufficient friction here, the frictional force, the static, for all the cases, the friction will counteract the applied force, so that the center of mass will not accelerate along x direction, and the normal reaction will counteract the effect of gravity, so that the center of mass will not accelerate along y direction. Therefore, it is a clear-cut case of translational equilibrium. For this particular example, since omega is 0, alpha is 0. So, it is a clear-cut case of rotational equilibrium. So, in toppling, both the equilibriums are attained in this particular case. So, let us demonstrate physically. We take this block, apply force somewhere here, and go on increasing the force. The frictional force is always preventing. Sufficient friction is there. The frictional force will prevent the relative sliding, that is the static force of friction. When you go on increasing the force here, normal reaction here at present, when no force is acting from outside on the rigid body, on the cubical box along horizontal direction, normal reaction must pass through the what? Center of mass. Why? Because if no horizontal force is acting, when this force is 0, when the force is 0, then if substitute the value of this force 0, what you are getting? X is equal to b by 2. X will be equal to b by 2. The normal reaction will pass exactly at the midway. It will pass through the center of mass. When no force is acting, but when the force acts, the distance of the point of application of the normal reaction force from this edge point P will be equal to b by 2 minus Fy by mg is less than b by 2 obviously. And when this force is exactly this much, x will be equal to 0. And that is the condition for toppling. And when the force will be exactly equal to that, all the points will lose contact except the points on this edge. This edge will be in contact and other points will be losing contact from the horizontal surface. So, this is the condition for toppling. Then you can say that the body is about to topple. All points except the edge points. These are all the points on this edge are called edge points. This edge is in contact, but other part of the base of this rigid body will lose contact with this horizontal surface. Well, we can say that the body is about to topple. So, we have solved this problem by taking the center of mass as a reference frame, a reference point, writing the torque equation. Now, I am going to solve the same problem by taking the torque about this point. This point is stationary, this point also is stationary. So, here you can get the idea that whenever there is a horizontal force, normal reaction will never pass through the center of mass. In this example, when you are writing the torque equation about this point, S point, we are getting some mathematical advantage. That is the force of friction in normal reaction. They pass through this point, therefore, they cannot produce a torque about this point. The torque is produced by gravity and the applied force. The gravity produces the torque in anticlockwise manner because the gravity tends to rotate the box about this point in anticlockwise manner, and the applied force tends to rotate the box about this point in clockwise manner. So, this is the torque produced by gravity. This is the torque produced by the applied force. Normal reaction cannot produce any torque about this point because it has been shifted to this point at the time of toppling. When it topples, x will be equal to 0. The normal reaction is passing through this point. Therefore, this cannot produce a torque. However, always this frictional force passes through this point, cannot produce a torque about this point. So, let us take the reference point P and write the torque equation. Tau P is equal to alpha 0, because alpha is 0. Tau P is equal to torque due to the applied force plus torque due to the gravitational force plus torque due to the frictional force plus the torque due to the normal reaction will be equated to 0. As I told you, normal reaction passes through this point, cannot produce a torque, and frictional force passes through this point, cannot produce a torque. This normal reaction passes through this point only in the case of toppling. But for all cases, the frictional force always passes through that point. In this case, the applied force will produce a torque in anti-clockwise manner, but the magnitude will be equal to the perpendicular distance from this point onto the line of action is y into this force, y into this force minus k cap. And gravitational force will produce a torque in anti-clockwise manner. This is the line of action of gravity, and from this point, this is the perpendicular distance, and that's equal to b by 2. So, mj into v by 2, which direction? K cap direction. When it is added with this torque, we are getting 0. So, you are getting Fy will be equal to mg b by 2. And the force will be equal to mj b by 2y. Exactly same force we are getting. And the force will be exactly equal to this much, then the body will topple. Toppling means a condition when the normal reaction will pass through the edge, then the body is said to be toppled.